my name's Sunny, and I used to work for MySQL, and that's my ex-boss sitting there. Now I work for PingCap, which is the maker of TiDB. And Mattias and I, who both work for PingCap, will now talk about PingCap, its distributed architecture, and how it's scaled. It's half an hour is a bit short, so I'm going to rush through a few slides. If you have any questions or anything, feel free to hassle me outside. But that doesn't mean you can't interrupt me during the talk, and we can spend maybe the entire half an hour on one slide, because distributed systems are complex, and I'm fine with that. So one other thing is that the two of us are here. Our CTO also was supposed to be here, but he's probably enjoying himself in Brussels somewhere. So if he shows up, then we can talk to him also. He's written a lot of the code. Okay. So it's easy to set up and start. It's got a thing called tie up. If you download it, it's really extremely easy to set up a cluster on a laptop to kick the tires, and that's how I got started. And that actually impressed me quite a bit when I started at PingCap. It's 8.0 compatible. That's stretching the meaning of compatible a bit because it doesn't support triggers, events, and stored procedure. But otherwise, in practice, we haven't had people complain about making big changes to their applications. They've just sort of worked. So that's how we say it's 8.0 compatible. It's scalable by design. Some of the things I'll talk about in detail. It's a disaggregated compute and storage, so you can scale your storage to petabytes. You can have 100 nodes all writing in parallel. So that's its main architecture, its main thing. It's multi-tenant ready. I'll go through some of the SQL stuff at a high level, handling on how you can achieve it. It's very versatile. It's used by gaming companies, banks, for their online transaction processing, Airbnb type companies, Databricks. It's any kind of load you can throw at it, except perhaps time series. So it's reliable. It's been it's battle tested with hundreds of petabytes for 6, 7, 8 years now, and it's running critical apps. It's open source. You can go to GitHub and knock yourself out. And the TiDB's storage is written in Rust, which is what all the cool kids are using these days. So if you want to be cool, you can look at the TiDB source code. So these are some of the customers. I couldn't fit all of them in. And there's some logos I can't use, but I can mention like Airbnb, Pinterest, Plaid, LinkedIn even actually. LinkedIn is moving to this. So we'll skip these. So this is the reference architecture. This needs a bit of explaining because I get questions on how does it scale. People from a MySQL background tend to think that it's by adding nodes that makes it scale, and each node is a self-contained. Let's think of it as a complete, your entire data set is on one node. TiDB doesn't work like that. So each node is a collection of shards in normal parlance, which we call a region. But the regions are distributed, and each region is a raft group. So it can scale to any level because you're scaling little regions, which are, I think, 100 megabytes. And that's what gives it the main power. So it uses raft for consensus. So each of these regions is independently scalable. So when you add a new node, it will lazily copy the region which makes sense, and I'll get to how it makes sense of the whole thing. It has an optional thing called the tie flash, which is a bit like heatwave, I suppose, which is a column store, but it's optional. But the key difference here is that this is transactionally consistent. You can run the same transaction, can read the column store, which is this is eventually consistent. That is not. That is actually properly consistent. And why it doesn't have an impact on the storage nodes is because that's always a raft follower. It's never a prime. No primary is ever stored. And so if it goes away, starting it up again is quite straightforward. Just clone a node and off you go. What else? It's fault tolerant. It's across AZ, and I'll talk a little bit about how it does the distributed query across both of these later on. Okay, so a region comes from HBase, which was the original storage for TiDB. and they are replicated using the raft. I've mentioned this. Regions are stored on RocksDB, and there is one RocksDB instance per node, and the rows in a region are ordered. And that's how they are split. So the sharding is done for you automatically, unlike, let's say, Vitesse. In Vitesse, you have to manually do the sharding. So your SQL queries don't need to know where something is located. It just, you write a query, it automatically knows where to find the shards and assemble it and do all the magic for you. That is one of the things that it does well. So it has three components: placement driver, the TiKV storage node, and the TiDB SQL node. So these are also, so this runs its own raft consensus using etcd, because it has to. So this is the brain behind the whole thing. It knows where the regions are located. It knows exactly how to move things around. It has a view of the cluster. So it does all these things. And this is its data that it uses to make decisions. So from every node, it gets a heartbeat, which tells it the total and free disk capacity, the number of regions that are there. It tells it the data writing speed at which that node is working. It collects a lot of information to decide how to place the data. It has a volume of sent and received snapshots, which are used for replication. It keeps count of the node overloads. CPU, it monitors the CPU so that it can, when it distributes the regions, so that it doesn't overload. So the hot rows are automatically, regions are split. So it's very sophisticated in that way. Information you can see. Then for each region, it knows the location of the leaders and the followers, and the number of disconnected followers. So it's responsible for, if let's say a node goes down, it has some leaders on it, not all of them, some leaders. It will the raft consensus will elect a new leader. It will tell the PD cluster, and the PD cluster will then rebalance its the setup. It can move. Just to give you, let's say you have 4 nodes, one goes down and there was some shards on the 4th node. It will move some of the shards that were on on the 4th node from the other 3 nodes and redistribute them on the 1 and 2, on the 1st, 2nd, and 3rd node. This is an example in that. So I won't go through this. This will just complicate stuff. So it also has placement policies. So you can say I create a placement policy which is region these shards should be in region US East or whatever, and you can attach them to a table. And you can also use the alter table to change the policy, so it will automatically rebalance it for you. It's all driven through SQL. And then once you drop a policy, it goes back to its default policy for that table or for that schema or whatever. So it's not, everything can be controlled by SQL. Okay, so this is the main component, the storage engine. This uses RocksDB. It provides storage basically. And interestingly, the transaction system is also implemented in TiKV. So it's the heart of the distributed transaction system. It uses Percolator for, it implements a variation of Percolator for distributed transactions. So the way to think about this is, you have a table, large table, and think of it as an ordered hash map. So TiKV is like an ordered hash map that is spread across your cluster. That's a way to visualize it. And all the magic on where things are located are in PD, and TiKV's job is just to manage those shards. That's it, nothing more. And the transactions. So this is an example. So imagine you have a table like key 1 to key 10. It'll split them into region 1, 2, 3. And there are 4 nodes here. So you notice that region 1 is on TiKV, like node 1, 2, 3. Region 2 is on 2, 3, and 4. But now, so if 4 were to go down, it will relocate 2 to 1. That was the point I was trying to make. So that's what PD knows, all this information. So raft, I'm assuming people know. I won't go over the details of raft, otherwise that's just a separate discussion in itself. But that's what it does. So this is the failure part. So imagine node 4 goes down and PD will then go, okay. So there'll be first step 1, node failure, it'll be a heartbeat interruption, it'll do a raft leader election again. One of the 2 or 3 will be the new leader, and PD will then create a third one on TiKV1. So that's the example. I won't go over this too much, it's too much. So because it's MySQL compatible, and it only implements read committed and snapshot isolation, TiDB maps snapshot isolation to InnoDB's repeatable read. There are some subtle differences. I won't go into now. They're online. You can read, but they're very minor. It shouldn't affect most apps. So we've gone over percolator. So the way the transaction at a high level works is that there is PD is also what we call the timestamp oracle. So it has a global timestamp for the start transaction and the commit transaction. And that's what's used for MBCC and for as part of the distributed transaction ID. So the SQL nodes that are doing query processing and everything, they act as the transaction coordinators in this case. So they know which storage node to go to. And it's also been optimized for single phase commit for small writes. By default, if you look at percolator, it's a 2-phase commit protocol. But it can be done, some small transactions can be done in 1-phase commit. The second phase is, let's say, but there are certain conditions. There's no secondary index, because the secondary index is part of the second phase of the build. And it only involves one region. So let's say you update one row in your transaction. It'll be a 1-phase commit. So for small commits, you get this optimization out of the box. The subtle point here is, the async is that if your secondary index dominates, then you will also get a speed up with async commit in TiDB. Otherwise, if that dominates, the time you save in that window is very small. It usually doesn't make a difference in practice. So the optimizer, this is very high level. So the optimizer, assuming you have a TiDB Flash node installed, the optimizer can figure out, even from parts of the query, which ones to send to TiFlash and what needs to go to the TiKV nodes. It can do that automatically. The price you pay, obviously, is you need to duplicate your data in the TiFlash node. So, but it does this automatically for you.
And the compression here is really good.
Its compression is fantastic. So, yeah, because it's a column store, and so if the cardinality is high, the compression is fantastic. So sorry, low. Okay, so this is the multi-tenant part. So if we have customers who are consolidating their applications. So they've got 5 or 10 applications running on Amazon Aurora, for example, and it's costing them quite a bit of money. So they want to, when they move to TiDB, they want multi-tenancy. So what they mean in multi-tenancy is have, let's say 2 clusters, but have 10 apps running on them. So the apps are all quite different. So some are very long-running queries, some are very short queries, and that causes problems. And you don't want the long-running queries to interfere with the short queries, because those are usually coming in from some kind of system where the query latency is very important. Whereas the long-running queries, they usually don't care. If it runs for 1 minute or minute and 20 seconds, they don't usually care. But they don't want that to affect that millisecond query, which is, I don't know, the shopping cart or God knows what. So it has a thing called a resource group, which monitors lets you control the usage of the CPU and I/O. I'll go over priority and burst table. So You can set high, low, and medium priority. The default is medium. Think of a priority here as an abstract. Think the low, medium, high, some kind of abstract thing like faster, slower. There's no absolute time to it. Burstable has actually a very definite meaning. Burstable is, let's say you have, as part of the system's running, some node has excess capacity. Maybe there's nothing running on it. Or the system, you've exhausted your quota, but there is still capacity in the system. Burstable means that use all the resources. That this query can use all the resources in the system if they're free. Otherwise, it is limited by whatever its our resource unit is. So if any query is tagged with burstable, it means that it must always run. And but in a general case, if it's got excess capacity, but it's used its quota, let it go. So it's got things like this. I think it's pretty good.
Sorry, good question. You said, the characteristic whether it is set on burstable or not on a per query basis. Yes.
Yeah. So it's at all three levels. I will get to. Let me show you. So it works at the statement level, session level, and user level. So how do you calibrate it? So it also has SQL for calibrating. You can say just calibrate resource, it does some default calculations and calibrates it. Or you can say calibrate from that time to that time because it keeps track of a lot of things. And so it will go over the load that the system was under at between whatever those, for the duration of 20 minutes starting from some time and recalibrate according to that load. The RUs for each statement session or whatever it is. So it also gives you a system for calibrating your queries or the resource groups. So it's got an example here, which is create resource group. If it doesn't exist, and give it like 100 or 1,000 and make it burstable. So now, and you can also, the information schema for looking at it, you can drop it, you can do all those things. And then you can attach the resource group to a user. You can use like the DDL kind of thing. You can set the resource group at the session level, the one that you created, and then you can use the standard hint mechanism for statement level. I'll probably skip this one, but this is like a high-level view of how the whole resource control stuff works. So it's got a bucket where it has tokens which it uses from whatever you were allocated, taken out from there. And they're kept in the metadata is inside the placement driver, which is PD. And it uses n-block-based scheduling. I think the paper was from VMware from about 7-8 years ago. That is used for calculating how to schedule the query based on the resource units. You can read it. I can probably send a link if someone's interested. Okay, this is another big thing. So in a distributed system, you want to use all the resources in your system. So you have, let's say, 100 TiDB nodes, right? And you want to do DDL, and you want to parallelize the DDL. So you want first have some resource control over it, so that's where the previous mechanism comes in. And then you want to, all the nodes involved, you want to involve as many nodes as you can without disrupting front-end load. So you have fine-grained control through this distributed execution framework to control how DDL runs. And it's all through SQL. You have very fine-grained control. So this, I think, is a very important feature for any large deployment. This is online DDL. So, Mattias, you want to talk about this? This is like stuff you work on.
So compared to what MySQL does,
I need water.
MySQL does take a metadata log, which means that there's one point in time where no transaction can access that table. So it needs to complete all the transactions that are touching this table, and then it will do the DDL final part, and then it will allow new transactions to start. And this is, at a large scale, that actually starts to become a problem. In a distributed environment, it's even bigger because it's a bigger environment. So the requirement there is we can't block any transactions. So what we want to do instead is to see how to solve that. And what TiDB does, instead of blocking the transactions, it allows sessions to see different version of a table. So it adds versioning to the schemas instead. And it goes by small changes in the schemas. It doesn't change just one column and removes it or adds an index. It has actually smaller steps and smaller stages in between. It basically has that you can always have the compatibility between the current schema version and the previous ones. That's how you're slowly migrating through the schema changes for the DDLs.
So one thing I would add to this is based on F1 Google schema change. So it's not some homemade, made up thing. So you can read the paper. It implements exactly what's in the F1 schema change from Spanner Google.
Yeah. And also utilizing the RocksDB SSD files. So instead of going through the whole overhead of inserting rows and so on through the transaction system, the RocksDB system, etc., we can actually generate these SSD files outside of TiKV and then just ingest those pre-generated SSD files directly into TiKV and RocksDB, which makes it so much more efficient. And this is used during DDLs and also when you're loading data for the first time.
Mattias, does that not generate a problem that you're generating extra storage temporarily for the new data during the DDL, which sometimes can be a problem?
Yeah, so that's a bit where the distributed execution framework comes in. How you configure that? Either you can have some extra TiDB nodes with more disks, so you can have more disks for generating these files and so on. But you can configure them as you like if you have the extra space on all the TiDB nodes or just the specific set. I mean, TiDB nodes, the SQL node is super fast to spin up and down. So you can even just add more nodes with disk when you're doing a larger DDL, and then you can take them away again.
Okay.
For example.
So one of the things I forgot to mention about the history. So TiDB came about and is written by people who actually manage large systems. So it is designed to reduce the pain of managing large data. So the people who've written this have felt that pain. It wasn't a theoretical exercise for them or some ego trip. They felt the pain and they did it. And all these things are from their experience.
And yeah, here's just an example of it's adding an index for a 10 terabytes table, and we do it in this cluster for under an hour, around an hour if it's a 10,000 key index, for example.
So one thing that I forgot to mention is a very important part of the whole distributed query thing. I just couldn't speak. Where is it? Yeah, so it's the TiKV. So TiDB has something called query pushdown. So each TiKV node has like a SQL engine inside it. Why? Think of a join. That's a distributed join, for example. So it can break it down, push down, let's say an aggregation. It'll push it down to the individual nodes where the leader region is, so that that query can run locally on the node itself, consolidate the result, and send it back to the SQL node, which will do the join or whatever else it does. So that reduces a lot of traffic. It reduces network latency. So this is an extremely important part of the architecture of TiKV. It's called the TiKV coprocessor. I think the idea comes from HBase. The name and the idea comes from HBase. So
even for the TiFlash, it actually has the MPP, so massive parallel processing.
Correct.
Has its own something.
Yeah, it has its own MPP architecture for it's. There's just so much. I don't know how much to cover. That's the thing. That's why I'm trying to rush it a little bit. So
I think we were at the tools, because that's basically where we need to finish off. So
finish off. So yeah, that's why I was rushing it. Right. So it has all these tools for people that need this stuff in production for connecting to other systems. It's got TiDB's. It's got
The change data captures, you can stream all the changes to other systems, Kafka or another TiDB plugin, for example. Backup and restore, that's also open source. And the beauty with that is that it takes it in parallel from the different TiDB nodes, which means that it's quite fast of doing the backup, and especially it's fast for restore. So you don't have a massive single instance to take the backup. You can break it down in smaller ones, so you don't need to do it in parallel.
so tie-up is the main. If you want to use it, just go to tieup.io.
Yeah.
And it's got like one liner you need to copy, and within 10 minutes you'll have a cluster running on your laptop.
And it works both for like a playground on your own laptop, but you can actually use TiUp for setting up and managing a full cluster.
Like
as well.
1,000 node clusters.
And
So
of
it's a
course,
very powerful tool.
if you're more interested in Kubernetes, yes, we have a Kubernetes operators and so on as well. So we work in both bare metal or whatever you want to use TiUp for as well.
Yeah, so these are the usual
We're
sort of
quite on
things.
time, actually.
Oh, thank God. So we have another thing called TiDB serverless, and as a showcase of TiDB serverless, we have an application called OSS Insight. So you can go there; it processes 7 billion events from GitHub in real time.
It's a single table of
Single table of 7 billion rows, and it's in real time. With 300,000 rows, I think added every hour or 2 hours or something like that.
Yeah.
So that's what it was about. So any questions? Yeah, please.
In the event that there's like a massive outage or you have to restart the entire cluster for whatever reason, how long does it actually take to come back up and get everything synced up?
Starting it all up, I've never done it, so I don't know. It depends on the size, I suppose. So if it's like hundreds of terabytes, should be.
Second, I mean,
It should be
everything's
seconds.
already stable on disk, right? So TiDB, the SQL nodes, they are stateless. So they're super fast in scaling up and down, so that's not an issue. The RocksDB and the TiKV, of course, it uses all the caches if you completely take down the cluster. So the first warming up will take a bit more, but just getting it up and running, that's fast.
Yeah, so warm up time will be the cost.
Yeah.
Otherwise, it's a very important point. It's all stateless. The compute nodes are all stateless. So that's why you can just fire up a compute node and it just can connect to any storage node and go from there. So it scales.
And there's one more
Linearly.
thing that I want to add as well, and that's upgrading. That can be quite a big hassle. But in TiDB, the cluster, it actually has a rolling upgrade. So there's no downtime for changing version and so on. You always upgrade, and it will do it gradually without affecting the cluster.
Any questions? Thank you.